Here we go.
Yay. I don't know a lot of the folks here, so I'm going to go and start and introduce myself. I'm Bob Gerzoff, WK2Y. I'm the non-engineer public health statistician and been a ham operator since 71, and fell in with Nathaniel, I guess when he was first getting started. So I even got a lab coat out of him. So I'll go from here, and Ed, go ahead and introduce yourself. And you're muted, Ed. Ed,
I went off screen a little bit here. So yeah, I'm Ed, WX2R. I'm been a ham just about as long as you have, probably, and lived for many years in North Jersey, and now I'm ensconced here outside of West Palm Beach, and I'm handling public relations for HamSCI, as well as being on the RLPR committee.
Yeah. So. Where in North Jersey?
Fair Lawn, Bergen County. Mm-hmm.
Plainfield, Union County.
Yep. Okay.
Normand.
Yes, I'm Normand, V2 Delta Victor Golf. I'm located in Drummondville, Quebec, Canada, up north. I currently have an FLDG station running up, and I'm being a ham operator since 1974.
Kenzie.
Yes. Hi, I'm Mackenzie. My call sign's KO4GLN. I've been a ham for about 4 years now. I'm a pre-med student at Old Dominion University in Norfolk, Virginia, and I help out with the social media aspect of HamSCI.
Cool. Gary? Well,
yeah,
I good afternoon. Most folks know you.
Yeah, I think so. Since I've been hosting this call in one form or another for the last couple of years, but along the same veins as others, I've been a ham for since 77. So it's getting close to 50 years, not quite there yet. Retired double E, and just generally try to stay out of trouble by doing what I can to help HamSCI in its mission. Kuldeep, you want to go next?
Yeah. Hi, I'm Kuldeep, and I'm a postdoc at NJIT. I work mostly with the HamSCI data, and one of the main goal is to see the eclipse ionospheric effect using the HamSCI data. I'm yet to get a license, hopefully maybe in 2025. Yeah.
Dave.
Yeah, Dave, W60Q. Been hanging out mostly on the technical side. I am hosting a grape too. That's about it for me.
Bill.
Hi, I'm Bill, Kilo 8 Tango Echo. I'm the New Mexico ARRL section manager. Like Kenzie, I'm a new ham. I've been licensed since February of 1960. Had your parents met by then, Kenzie? No, didn't think so. Yeah. So I've been doing a lot in ham radio for a long time. I enjoy the science of it. I got to speak for NOAA and HamSCI at the total solar eclipse here in Albuquerque during the Balloon Fiesta a year ago, October.
You know N2GJ by any chance?
Jerry with a G, I certainly do. He's my section traffic manager.
He's a longtime friend of mine from back in New Jersey. So we'll carry on about that another. Yeah, I'll tell him you said that.
Yeah, go ahead. He'll like it.
Yeah. All right. Who's this guy, Nathaniel?
Hi, I'm Nathaniel, W2NAF. I'm an associate professor at the University of Scranton, and I started HamSCI when I was in grad school, and I've been a ham only since 1998.
Hey, Mary Lou.
Hi there, Bob. Mary Lou West, a retired physics and astronomy professor from Montclair State University in New Jersey. I was Nathaniel's undergraduate physics professor. I taught him everything he knows about undergraduate physics. Have been a ham for, I don't know, 20 years, something like that.
Kamal.
Hey, hello. I'm Gamal Zaid. I'm an assistant lecturer at the School of Computational Science and Artificial Intelligence. I am now putting hands-on modeling, some optimization, and learning AI. I'm very glad to work under Dr. Nathaniel's supervision in voluntary research. That's my story. Thank you.
Ron?
Yeah, I'm Ron. I'm a nurse RN case manager, and I joined HamSCI, I think it's been about 6 years ago. And I kind of come in from the non-scientist citizen science level, and have been very graciously welcomed in, have been active. I really enjoy writing and speaking, and so I've tried to play up to what I think are some of my abilities and write some articles with magazines under tutelage of some of the folks here, in particular Dr. Frizzell. And then I do presentations, mainly Zoom, all over the nation, kind of an entry level for ham radio operators and astronomers that don't have a good basic foundation in some of the sun and the ionosphere and magnetosphere. And so I do quite a bit of those and just tag along with the group. So
Thank you. Dave? McGraw?
David McGaw, N1HAC, Canaan, New Hampshire. I got interested in amateur radio in the 60s when I was young, but didn't get a license till 89, but I still qualify for the Quarter Century Wireless Association. And then I'm a research engineer at Dartmouth College, and we do radio propagation research and emissions from the aurora and the radiation belts and all that kind of stuff. And I'm also vice president of WNFN Twin State Radio Club and repeater manager. So I've got my fingers in all over the place, and an active member of HamSCI, of course.
Hey, Gwyn.
Hello, Gwyn Griffiths, G3ZIL, licensed since 1970, retired oceanographer, worked closely with Rob Robinette, a very good friend, AI6BN, on Whisper Demon and propagation studies. And for everything else, I refer you to the excellent article by Mary Lou in the even more excellent first edition of the HamSCI newsletter.
Great.
Thank you, Gwyn. It was fun getting to know you.
Ed. N3ED.
Hi, this is Ed. My wife Gladys and I have been attending HamSCI conferences since the beginning of the COVID, when the conference got suddenly transferred to online. As a ham radio operator, I've been a ham for a large, probably since the beginning of the 1970s, near the beginning of the 1970s. I also have a first-class radio telephone license, which got converted to general radio telephone operator's license since the end of the 1960s. And I have worked actually with the University of Delaware and NASA on projects, including citizen science projects in the early 1970s. So I I have an interest in this and in radio astronomy on an amateur basis. Back to Ned.
Hey, Gareth.
Afternoon.
You want to say, do you want to do a quick intro for those who may not know you?
Yes, sorry. Hi, Dr. Gareth Perry from NJIT. I'm late. As you can see, I was just lecturing students and they were pointing out errors in one of my examples, which kind of stitched me up for about 10 minutes. But anyways, I've been with HamSci, I guess, almost since the founding back in 2015, I think it is. And Nathaniel and I wrote some papers on looking at ham radio transmissions from low Earth orbit satellites, and now I'm leading, along with Nathaniel and some other folks on the call here, some research projects related to the eclipse and hopefully transforming or evolving. I don't mean that in a negative way. HamSci into a cooperation that can target other space weather events that aren't the eclipse, notably, geomagnetic storms or meteorite storms or something like that, meteor showers, I should say. Yeah. Call sign is KD2SAK, and I'm general, licensed as a general, but I don't get on the air as much as I need to. Back to Net.
Okay, let's see. WX2R, Ed, we went through you. Ed, I think we did you. Ed Dunlop. Tony Rogers. Hello, Tony. Okay. We'll come back to you in a moment. And let's see, Scott, are you there? Okay. They are just lurking. Scott disappeared. Okay. Nathaniel, I'm going to turn it back to you because I believe you have an agenda for this meeting. And let you introduce Kukai.
Sure. Thank you very much. So next week, many of us are going to the American Geophysical Union conference in Washington, D.C. And if you want to see what HamSci is up to at the AGU conference, you can just go to hamsci.org right now and can share the screen. And there is a HamSci at AGU 2024 link there, and it has a list of all of the presentations that will be given by HamSci or of interest to HamSci. Also on the website, I see that this was just updated. It's very exciting. The HamSci 2025 workshop is going to be held at NJIT, and they have the new banners up on the website. So you can go there, and it tells you what date it's going to be, and it says to check back at the website in January 2025 for more information on how to register. But I'm very glad, thank you, Gareth and the NJI team, for getting that up. So along with the AGU conference coming up, one of the people going to the AGU conference is the new postdoc at Scranton, Dr. Kukai Hazumi, who has been working on both modeling of HamSci amateur radio observations, and she's also doing a project looking at how equatorial plasma bubbles affect radio transmissions, HF radio transmissions. So what I will do is I will turn it over to Kukai as soon as I can figure out how to stop sharing my screen, and we'll let Kukai tell you about all the wonderful work that she has been doing. So take it away, Kukai.
Okay, thank you, Nathaniel and Gary, for coordinating this telecon to be possible today. Thank you everyone for your time. So this is Kukai, Nathaniel postdoc. I'm very happy I can be a part of HamScience in last year. So okay, let me share my screen. Can you see my PowerPoint? Yes. And is it in the presentation mode now?
Yes.
Okay, perfect. Very nice. Okay. So, okay, today my talk is about exploring our RBN Whisper PSK reporter for studying equatorial plasma bubble. And okay, I think, okay, let me change the mouse to the pointer first. Okay, can you see my laser pointer?
Yes, we can.
Yes, perfect. Thank you. Oh. Okay, so let's start with the global ionosphere. So as many of you know already, the ionosphere has large structure and large day-to-day variability. And as you can see, these two dense region with red color moving to the westward direction. This is the region called EIA or equatorial ionization anomaly. Okay, so what is the EIA? EIA is the region of a dense electron density in the northern and southern magnetic hemisphere of our Earth. So it was due to the Fountain effect. So Fountain effect consists of two process. First is E cos B drift at equator. So normally E go to eastward direction, right? And B to the northward. So E cos B drift show your give your upward drift direction. So it means that it's push up the plasma or electron to the upper region or higher altitude. But at the same time, there's a thing called the gravitational force. And the gravitational force also try to pull those upward plasma down to the lower altitude, and it's diffused along the geomagnetic field line. So at the point where the upward direction and downward direction has balance, that point show the most dense electron density in northern and southern hemisphere of the Earth. And that point, that two point or two crest called the equatorial ionization anomaly. That normally can see around plus minus 15 degree from the deep equator or magnetic equator. Why I mentioned it? Because it has a link to the equatorial plasma bubble, the topic that we are interested today. Okay, so what is equatorial plasma bubble? Plasma bubble is a product of the three electrodynamical processes. First is the amplification of the upwelling during the post-sunset rise. It means that after the after the sunset, the F layer at the bottom side keep lift up to the higher altitude, and this called the upwelling. So you can see that the upwelling will cause a wave-like structure at the bottom side of the ionosphere like this. And then one is lit at certain altitude with certain conditions. So the first plasma bubble will launch from the upwelling crest like this. And as the time progresses, the structure inside the bubble will keep developing inside the bubble. And it's even see the second, third bubble in the same upwelling like this. And it will keep propagating eastward. So this is a kind of plasma bubble. And normally bubble one is its structure leads to the higher altitude. At the same time, there is a magnetic field line. So it's the plasma inside the bubble keep diffusing along the magnetic field line so that irregularity structure in the bubble can reach to the higher altitude and latitudes at the same time. Okay, so why is important? In the quiet time, ionosphere normally introduce the ionospheric delay to the radio waves when it's propagated through the ionosphere. But during the plasma bubble exists, so once the wave propagates through it, it introduced the scintillation into the radio wave. And once the scintillation level is too high, it means that the signal to noise ratio is very low. In the worst case scenario, it means that the receiver could not receive the signal due to deteriorated signal. So yeah, this is a simple explanation. But scintillation normally happen anytime in the day, not only nighttime, but in the daytime also. In the daytime, the cause of which normally is sporadic E, but at the nighttime, the cause is the equatorial plasma bubble, which is our focus of today's talk. Okay. And there is a report of the accident in the real world related to the plasma bubble. So there was a critical masses on the battlefield due to the plasma bubble. So this kind of thing can happen with the civilian communication as well. So that's why we also should study on the plasma bubble and its effect on radio communication. So how the bubble look like when we look it from space? So at the left side is the image taken by the astronauts on board the International Space Station. This is raw image. And at the right side is the same image, but multiplied with its red channel about 15 times to emphasize the red emission due to the atomic oxygen in the F layer. So as you can see here, you can see the wave-like structure here. This is upwelling at the bottom F region. Here. Can you see? And at the peak of the east upwelling crest, you can see a tube light here and here. This is a plasma bubble from International Space Station. We can see it's really clear like this. Okay. But at the in the tube that is considered a plasma bubble is not empty tube. There's a lot of wave structure inside the bubble. That's why it has a different effect on the different frequency of radio wave. So this is the simulation result from high resolution bubble model. As you can see, so this is the upwelling. You can see the upwelling keep propagating eastward like this. And you can see at the top of the upwelling, you can see the bubble keep developing its structure like this. And you can see 3 bubble from this upwelling, 1, 2, and 3 like this. So there are many bubble in, there are possible many bubble in one single upwelling. Okay, and the distance between each bubble normally around 50, 60 kilometers. Okay, so how does a HF wave propagate during the plasma bubble event? So this is the at the left side, this is the radio wave at 20 megahertz launch into ionosphere when the plasma bubble exists. You can see that bubble has like almost no effect at all, as you can see here at the left figure, because the frequency is high enough to, just keep penetrating and go beyond those structures. But at the right side is the bubble structure with 5 megahertz radio wave. So you can see that some waves just bounce back from ionosphere, bottom side ionosphere as normal like this. But some, when it's penetrated to the bubble structure, is keep reflecting here and, has a second bounce here like this, or sometimes the wave was trapped inside the bubble. Sometimes it keep reflecting, sometimes it's got darkened like that. So this kind of thing cause the radio wave that we can receive at the ground has a, has a very wavy structure of the SNR when we see the SNR of the radio wave. And it depends on where the wave was reflected back to the earth. If it's reflected, for example, if you can see here, in normal situation, if the ionosphere at the bottom is flat like this, it might just go and reflect and go at the same angle. But with some tight ionosphere, so sometimes it, reflect back to the earth, bounce back to the earth, but with the smaller angle, depend on the angle of the bottom side ionosphere. So sometimes the station that is not expected to receive the signal can receive the signal, whether it's nearer than normal or further than normal, depend on the bottom side structure of the ionosphere. So yeah, so it depends on the perturbation size and structure inside the plasma bubble itself. Different frequency always have different propagation response and effect. So this is a kind of open question that what frequency range in HF band is most suitable for nighttime communication in low to equatorial latitude and why? Okay, so in order to confirm the existence of the plasma bubble, I use the HFTP experiment. HFTP is high frequency trans-equatorial propagation. So the receiver is in ORI in Japan, and the transmitter is the Radio Australia in Shepparton, Australia, and frequency of which is 10-ish megahertz. But now it's already stopped its transmission already since it stopped in 2017. So we use the data in the past when it was available. Okay, so for the TEP data, because they have a lot of antenna for the direction finding purpose. So at their raw data, they use the music algorithm to estimate the direction of the arrival angle of frequency. Then they convert it to the TP data that contains a timestamp, azimuth angle, elevation angle, amplitude, and frequency at the receiver. And once we plot the data as a function of time and azimuth angle, we can see the data like this. At the left is with the signal intensity, and at the right is without signal intensity. And the data available in this website, data availability are from is from 2003 to 2018. And normally we can see two types of data. First is discrete off-grid circle signal, and second is diffuse off-grid circle signal. Let me explain a little. So as you can see here, receiver is to the north of the transmitter. So to the north of receiver is considered 0 degree, and to the south is considered 180 degree, because transmitter is to the south. So we expect to receive the continuous signal around 180 degree. So this one is the signal that we receive directly from the transmitter. But when we see this kind of off-grid circle signal, and normally we can see it as a downward or counterclockwise displacement as a function of UT. It means that we see some structure. I will explain later what is it. And this is called a discrete off-grid circle signal. And for the diffuse off-grid circle signal, so normally it's distributed widely in the azimuth angle and without obvious pattern. Okay, so how to interpret it? So at the left side is the HFTP data. So this quite straight line is the great circle signal, and you can see two striations here, 1 and 2 here. So it means that we can see two striations and they are moving in counterclockwise direction. Why? Because as I mentioned, to the north is 0 degree, to the south is 180 degree, to the left or to the west is 270 degree. And we can see the signal from, for example, 210 to 180. It means that the wave arrive from 210 somewhere here and 280 somewhere here. So it's like it's moved like this. It's moved from west to east or move in the counterclockwise direction. So this kind of movement of the structure in the ionosphere is very well along with the movement or propagation of the upwelling or the plasma bubble, and it should be over the Pacific Ocean due to its direction and the distance. So we interpret that these should be two plasma bubbles over Pacific Ocean and is propagating eastward. Okay. So the right part is just keep showing like when bubble moving, the angle of arrival will keep decreasing like this until it go to around 180. So we can see this kind of situation. So I use this kind of information to classify whether there is a plasma bubble or not to confirm existence of bubble on each day. Okay, and to study plasma bubble, we need the data coverage in equator and low latitude region. However, the land is very limited in low latitude, and therefore continue in both temporal and spatial coverage of the data is very significant, but is still lacking. So we try to find a way to improve data availability and coverage, and we think that HamSCIence has a very good potential to do so because, for example, in this plot, this is a HamSCIence ham spot data. So you can see a lot of data available in the global level, but this is in 2024. So we think that if we can use HamSCIence for this kind of study, it would be very nice. So I use the HamSCIence for this study, and the data can be downloaded directly from medical database. Okay, so the data selection and criteria. So first, both HFTP and HamSCIence should be available, and we choose the solar activity in the high solar activity years and in equinox season, which is the active bubble season. So finally, we choose the year 2013, 14, and 15 in months February, March, April, August, September, and October. So in this time period, in total, we have 461 HFTP image, and I categorize it into bubble on and off day and other groups of pattern. But we are interested in plasma bubble on day, which are 68 image. Okay, for HamSCIence, I select the transmitter and receiver of HamSCIence within 90 to 180 degrees east in different magnetic hemisphere by selecting the transmitter to the south in the southern hemisphere and receiver in the northern hemisphere to, equivalent to what TP has. And then I calculate sunrise and sunset time at the F region because the bubble is a kind of nighttime phenomenon. And I also calculate the angle of arrival of HamSCIence at each receiver. Okay, let's see the result. First, at the left side, show the no plasma bubble days, and at the right side is a plasma bubble day. Okay, so this one is the HFTP. So you can see it's very clear that there is no plasma bubble on this day. But at the right one, you can see there is a striation here. So there is one plasma bubble exists. So this is plasma bubble day, and its bubble was seen from TP around 12 to 17 UT. So I just put a mask on the data. Okay, and okay, so for the HamSCIence, the top panel show the angle of arrival in azimuth degree, and x-axis show the time in UT. This is 1 day plot. And the circle mark show the nighttime data, cross mark show daytime, and triangle show the terminator, whether it's the sunset or sunrise terminator. Okay, and the middle three panel show the geographic distribution of transmitter and receiver. The receiver are shown by the square red mark, and the transmitter in the southern hemisphere are shown by the blue circle marks. The most left show all day data. The middle one show the nighttime data, and the right one show the data at the terminator. Okay, and it's the same for other days. And so at the bottom, I recolor the no plasma bubble to the green color, and with plasma bubble to the orange color, and overlay it together like this. So at the left side is the no bubble masking over the plasma bubble. So you can see that in the interested period of the day, you can see that in this circle, 1, 2, and 3, you can see that HamSCIence can receive the signal on the bubble on the why they cannot receive at the same arrival angle and at the same time on the bubble off day, like this. So at the right side is the similar thing but in reverse order. Okay, so this is the 2014 in February 19 and 22nd. Okay, one more case. Similarly, this is on 19. So for the bubble off day is the same day, but for the bubble on day is 1 day later. So I did all the same process, but on the February 22nd, you can see there are 2 bubbles here. Okay, and the time is around 11 to 17 UT. You can see that yeah, there is some angle of arrival on the bubble day that we cannot see when there is no plasma bubble day. But you know, on the other hand, we can also get the angle of arrival from the plasma bubble off day with green color here, while on the bubble day we could not receive signal from this angle as well. Okay, and next one is the different plasma bubble off day as a reference. So next one is the reference day is April 12, and bubble on day is 22nd, the same as the first case that I show you. Okay, so similarly, this is one plasma bubble exists here. And if you look at the bottom left figure, you can see that the green one show the arrival angle on the plasma bubble off day like this. So we cannot see this kind of thing on the plasma bubble on day. And on the other hand, we can get the signal around 150 degree on the bubble day, but we cannot receive this kind of signal when there is no plasma bubble, for example.
Kukai?
So this, yep.
What frequency are we looking at?
Oh, okay. So for this one, for HamSCIence, this is all frequency plotted together.
Okay.
Okay. So yeah, similarly, this is the bubble on day on 23rd and the bubble off day on 12th. So we can see this kind of thing repeatedly, but it's not so obvious. Okay, this is for 2014. So, okay, so I bring it together here. So I put the bubble off day 2 day overlay together and bubble on day 2 days overlay together like this and put it in order. So I focus on the left plot when no bubble masking over the bubble days. Okay, so we can see that here there's the angle of arrival when we can receive only on the plasma bubble on day, while we cannot at the reference bubble off day. This is the example case in 2014. Okay, next 2015. So I did the same thing. So at the left side is no plasma bubble day. At the right side is with plasma bubble. Then change it color and put it overlay each other. At the left side, top left figure is no plasma bubble on February 23rd, 21st, but in 2015. So it look like this. And at the right is on the next day, but with plasma bubble. And at the bottom is for September, with and without bubble, and in the same week. And when I overlay it together, you can see that we can see the angle of arrival that we receive only with bubble at certain time at night time here. And also similarly in September, we can get the similar thing here. It's of course not obvious, but it's what we can see right now. Okay, so so let me summarize this talk first. So we try to develop the method to retrieve the angle of arrival at each HamSCI receiver. And we make a comparison of HFPP and HamSCI angle of arrival from 2014 and 15 as a preliminary result. And on the bubble day, although it's not obvious, we observe the presence of angle of arrival during 13 to 20 UT at a zenith angle that are not observed on the bubble of reference day during the same time. So we are not quite sure yet about what we can see. And because the data density in Asian region is not so good, so we think that shifting the focus to another region like in America would be better and might help us yield better result. Okay, and that's all that I wanna show you today. Okay, thank you.
Thank you so much, Kukai. This is great.
Thank you.
This is Ed. I do have a couple of questions, if it's okay.
Yes, please go ahead with questions. And we should note that this is very, experimental researchy sort of work. So these are some of our first efforts and Kukai's first efforts to look into this sort of thing. So we are certainly open to suggestions and questions and all of that sort of thing. So go right ahead.
Well, my first question is, I'm assuming that by HamSCI, you're referring to the various ham radio, whisper, and other records of transmission and reception.
Yeah, so HamSCI that I mentioned include the Whisper, PSK Reporter, and RBN that are available on the medical database.
Okay, so the reason I was asking that question is to define what the frequencies and wavelengths were. One of the things that I would like to help you, maybe you can make clear, is normally when ham radio operators are talking about their antennas, when they refer to angle of arrival, they're talking vertically. And I gathered from the presentation that you're talking about the horizontal azimuth with 180 degrees being where the transmitter or receiver is located, where the transmitter is located.
I see. Thank you.
Okay, now my other question is, because we've defined the approximate frequencies that this is taking place, how accurate is your angle of arrival, and how are you calculating that?
You mean from TP or from HamSCIence?
Yeah, I'm talking about not a gigahertz or a gigahertz and a half. I'm talking about the ham radio frequencies of between 1 and let's say 30 megahertz.
Okay, how I derive the angle of arrival is very simple for now. So we know the transmitter and we know the receiver, and we don't know other information. So is the azimuth angle from the receiver when we look to the transmitter? This is the angle of arrival.
I think what we're trying to do here, it's a little bit different from what might normally be considered angle of arrival. What we're trying to do here is almost show how the propagation might change as a function of azimuth as a bubble or time goes through. And the idea is we're basically imagining you have like one transmitter, down in the southern hemisphere, and then you have a whole blanket of whisper PSK RBN receivers in the northern hemisphere that are spread out in azimuth. And and if and the hypothesis might be that if there's no um if there's no plasma bubble, if there's no equatorial plasma bubble, then you'd get predominantly great circle path propagation, and so you get the highest signal to noise ratios, or the most links appearing just in along the great circle path. But if you had an EPB move through, then maybe you wouldn't get the most receptions along the Great Circle Path. You'd get the most receptions either to the east or the west of the Great Circle Path.
Okay, that's a great explanation. So that also led to my next question, which is, does this require activity in both the northern and southern hemispheres?
Yes, we do require both data in northern and southern hemisphere, because the transmitter and receiver should be in the different hemisphere, and in order to study the wave propagation with the plasma bubble.
Okay, and I'm going to end my questions there and only make one very slight comment question, and that is, when you did you showed photography taken from the International Space Station with essentially a single lens reflex camera. As an astronomer, I know that in many cases, there's a filter that's inside that camera that is designed to limit the spectral bands to what your eye can see. Many astronomers take that filter out in order to increase the spectral range of the camera into the infrared and ultraviolet. Because the sensor in the camera is capable of that. And so it would be valuable to know whether or not they have removed that filter in taking those pictures and in processing it. Because the physical filter makes a difference in how the image appears. And that's just a comment to let you know that problem exists.
Okay, this is just comment. That photo taken when I was the PhD student, and my lab has a collaborative work with the astronauts in the ISS, and those kind of photo was taken without scientific purpose at the beginning, just for recreation of the astronauts. But we just try to make it for scientific research. So we just try to find a way to use it. So I think that is what with the just simple and normal setting without, any extraordinary setting at all.
Which I think that's neat because it's also kind of in the spirit of what we're doing with the ham radio data.
Yeah.
Yeah, thank you very much.
Okay.
And
Would there be, oh, let me start with, what is the time frame of those signal shifts? So as a bubble moves through, am I looking on the scale of seeing a shift from 180 to 160 within 5 minutes, within 15 minutes? How long would it take for a bubble to be manifest in the data? Or do you have a guess for that? Or
I think that it would be depend on the plasma bubble propagation speed, and it is about the same as the background wind. Okay. And we know I don't remember perfectly now, but we normally maybe about 100 kilo. No, I don't want to say because it might be misleading. But okay, let's look at this TP data. So this is a real data, so it's reliable. So you can see that bubble propagate from around 210 or 15 degree, and it's moved to around 180 degrees. So this take around from 12 to 17, so it's 6 hours.
okay. And we would not see, do we expect to see any effect in non-transequatorial propagation? So east-west propagation, US to Europe, would there be any potential effect?
If it's US to Europe, maybe the latitude is too high without geomagnetic storm, because normally bubble has a limit boundary within the EIA crest, and that EIA normally is just about plus minus 15 degree from the magnetic equator. But with geomagnetic storm, sometimes this limit just extend further to the higher latitude. So those when those events appear, happen, so we might be able to think about US Europe east-west propagation, but it's not the simple case or the general case that we can expect, I think.
Okay. Well, I have a million questions, but I'll put them in an email. But one last question. Do we have any guesstimate for a theoretical maximum on the signal to noise decrement that might occur coincident with this shift? So if I go from 180 to 210, as in that illustration, do I know what kind of signal to noise ratio decrease or possibly increase I might expect?
There are explanations for both increase of SNR and decrease of SNR. For SNR increase, I don't think it's increased, but it's just higher than normal reception level because of the shorter distance of the wave propagation. So that is the explanation why we can receive a higher signal to noise ratio once the wave was bounced back from a kind of upwelling crest with some certain angle. So it leads the nearer
it's
distance.
more, it would make the signal to noise ratio more variable with time, right?
Yep.
Yeah, more highly variable.
Should be very fluctuation, should be very variable.
Hence the term scintillation.
Yeah, as a function of time.
And
so,
go ahead, Nathaniel.
Yeah, no, you go ahead first.
I was going to say, but we don't know. I mean, we expecting 3 dB change in 10 dB change, 20 dB change, maximum of 20 dB or 30 dB. Do we have a sense of what that might be?
I would think it would be frequency dependent, wouldn't it? Also,
probably.
Yeah,
it'd have to be. And bubble
not
dependent.
and even with the same frequency, it does not show the same response for every single bubble, because every bubble has different characteristics. That's why.
Yeah, different shape, conformation, whatever.
Yeah.
Okay. I'm wondering if there's might be a theoretical maximum, but that could be calculated. But
So I think these are all really good questions, Bob. And I should say, this just a little history of how we came up with this particular project when we were trying to find funding to get Kukai to get started here. We were trying to look for something that kind of matched her previous experiences with what with the data sets that we had, and we were also working with another scientist at the time. And Kukai came with this experience with this HFTEP experiment where she's showing these red plots that you see on the screen here. So we tried to imagine a possible way that we might be able to create an equivalent sort of display using the existing WhisperNet PSK reporter RBN data. And we imagined this particular approach kind of similarly to how I'm doing the LSTID approach with this same data set. And so and that's where we've gone with this so far. I think we're just getting started with Kukai, and she's going to be in the process of writing more grant proposals to continue her work in the future. And I think all of the questions that you're asking, in terms of what the signal to noise ratio variability is and things like that, are all really good questions that she might be able to work on in the future. The other thing I was really hoping that Gwen, if you're still listening, I was really hoping that you would be able to see this presentation, because I think there's tremendous opportunity to study this with a Whisper Daemon, because I think there's going to be not only variability in signal to noise ratio and um, just whether you hear the signals or not, but I thought it might also affect the Doppler shift and spreading, and this might be good justification for setting up Whisper Daemon stations in both North America and South America, and trying to look in that TEP area and build out the network there. What do you think, Gwen?
I do indeed, and if I had a question, the first one would have been if there was a Doppler signature of the fountain effect, and whether it's traceable against a background. And what we know from the Personal Space Weather Station spectrograms is that multiple propagation modes can be identified by different Doppler, even though they coexist. They have separate Doppler space. So I think that could be tremendously powerful. There's possibility, looking at your map with the magnetic equator, for Costa Rica to southern Brazil. That might be I'm sort of looking at that. So it's not as great a span as Japan to Australia, but if Costa Rica to Brazil is suitable, we do have a whisper sonde from Paul in Costa Rica and some Whisper Daemon receivers in Brazil. So that would be one thing to check. And so absolutely, we can look at that. And for my understanding, if I may hold it for just a minute, slide 10, it looked as if the reflections or refractions were really from the hole left by the plasma bubble fountain, rather than the plasma bubble in the higher ionosphere, or is it really from both?
Because it's at 5 megahertz, so mostly it's the reflection was due to the upwelling at the bottom side of the ionosphere and the bubble. But if we go beyond, sometimes we can see the wave keep trapped inside the bubble structure. So it really depends on the frequency and depend on the what bubble structure that we use as a propagation medium.
Okay, thank you. And thank you so much for a wonderful talk, okay?
Thank you.
Are there any other questions for Kukai?
I had one. That's
Go
a
ahead.
really great talk. Right. So first of all, we are starting with HamSCI data incorporating into spreadf. That's really great effort. I wonder how we tackle the freshly generated spreadf and the spreadf which are moving along the east-west direction. Do we have any idea how we will try to tackle differentiate between the spreadf which are freshly generated over a region and the ones which are moving from east and west direction?
I couldn't hear you well, but did you ask me how we distinguish
Yes.
between the
How we
bubble is
distinguish
moving?
between the bubble which is moving east and west and the one which is freshly generated over a localized region? How can we distinguish between them from the HamSCI data?
It's still difficult question because for now we still cannot see the obvious signature of the bubble itself on our HamSCI yet. Okay.
Yeah.
I'm kind of thinking, what I was suggesting for next steps with this is that, Kukai, move from looking at the data in the Asian sector over to looking at data in the American sector, because we know there's a tremendous amount of traffic between North and South America on the amateur radio bands, and that we maybe move to some newer years, and we also look at events that have already been studied with in with the equatorial instrumentation in this hemisphere, and then look at those particular events to see if we see some more obvious signatures in the amateur radio data. And you've been starting to do that a little bit, right, Kukai?
Yeah. Yes,
Yeah.
already. Yep.
Yeah. Well, I think it's 5 o'clock now, and I think we should probably wrap up here. And but I want to thank Kukai again, and I'm hoping that, like, for many of these things, this is just the start of a conversation. So this is kind of introducing a new topic to HamSCI. We haven't really done equatorial plasma bubbles before, and we haven't really done this particular type of phenomena before. So I think there's really a rich data set here that could be explored with some new topics. So I think I'm hoping that we can continue this work in the future.
Yeah, I agree, and I think this presentation has been great. And I think you might consider setting up from time to time some sort of a presentation type where pre-presentations quietly get presented and get this kind of feedback and conceptualization in order to move the research forward. I think this was great.
Thank you. And I hope to, participate more with HamSCI community.
Yeah, I would think, I know we would all welcome that. The one thought that's coming to my head is to present an analogy real quickly. As many people, billions of people have smartphones. When they communicate with those, they send each other photos or texts and stuff. They have absolutely no idea about the infrastructure that makes all that happen. Myself speaking as a ham, I've got 100,000 contacts in my log. How many times I've hit the key, made a transmission, received a transmission, I had no idea what was going on up there in the ionosphere. And there's a heck of a lot more going on than I think most of us realize. And it's really fascinating to sit here and watch some of these theories come forth, and then hopefully see them proved out and so on and so forth. But it's sometimes a simple view is okay, but we also have to realize that we're very, very lucky that all these things can happen, and we can utilize them to communicate. It's really something.
Okay,
All
Nathaniel,
right.
you have to show the short skip.
The short skip? What? This one?
That one.
Hi. Kukai has one too.
Yeah, unfortunately, he's at daycare.
Yeah, he's a big. And Kuldeep, do you also have one?
Yeah, 10 months old.
10 months. So yeah, we're all. So we have all these harmonics that are popping up.
By the way, talking about different modes of propagation, this morning we were having a conversation about eclipse that's coming up August of 2026. That's a polar, goes around the North Pole, and it might be a very interesting study in polar propagation, which is a whole other beast.
Yeah, there's
Yes.
there's a sailing vessel going up around Iceland, north of Iceland, and the fare is only $24,000 a piece. If many of you would like to take that, I'm not.
It might be good to get a radio on there.
Right. If anybody wants the schedules for eclipses, both partial and total, I have them, and the tracks and everything.
All right. Well, again, thank you, Kuka. I guess we'll try and wrap up the call since it is getting a little bit late. Thanks everyone for participating, especially for all the questions. They add a tremendous amount to the discussion, of course. And hopefully we'll get an update in the future to see what when the research moves toward the Americas and refine your techniques a little bit. So if there's nothing else, anything else?
What's our schedule for the next week or two or month? Do we have one?
No, we don't. I know obviously a lot of you will be gone next week to AGU.
Yes.
And then it's the
Holiday.
academic calendar. I know takes about a month off, and I was wondering if you needed a break because it's been HamSCI's big year, right? We just saw that.
Yes, it is HamSCI's big year. That's right. So the conference at NJIT will be HamSCI's big year. I can tell you right now that next week I'm going to be at AGU, and so will many of the other academics and some of the volunteers will be there. And then the week after that, I actually have some committee meetings for the university that I have to participate in that Thursday. So I probably won't be able to make the 19th. And then the 26th of December is the day after Christmas, and I think we should all be participating in some sort of conviviality with our local family and friends. And same thing for maybe the day after New Year's. So maybe we take a break until say January 9th, perhaps?
That was the decision reached on the grape call this morning, the same date.
Wonderful. Well, I guess we're all in good agreement there. So in that case, I wish everyone Merry Christmas, Happy Hanukkah, Happy Holidays, Happy New Year, and whatever else you may celebrate. And I'll see some of you at AGU, some of you I might see in the Monday night telecons on the listserv. But I do want to thank you and all of the community members here for all of your wonderful participation. That's really what makes HamSCI HamSCI. And I really appreciate it and greatly enjoy being able to spend time with all of you. So thank you.
Happy holidays.
Thank you.
Have a great month, everyone.
73.
73.
73.
73.